when t going to infinity, then upper bound is 0. So we have only lower bound. That is 1 plus rf squared, then parenthesis x squared 0, then divided by 4a plus bf. Agree? You have to understand this equation first before we go on. Otherwise, you will get lost. All right. If that's the case, that's my feasible cost index. Remember, now, this J, this cost index, only valid when A plus BF less than 0. Agree? All right. Now, if I minimize the cost index with respect to F, partial J over partial F, if I minimize that, and I partial this, partial J, partial F, if I do that, that's, if I want to minimize cost index, what does that mean? I minimize cost index. All right. So I have, say, partial J, partial F. If I that is equal to 0, that means I minimize the index. Right? So if I do this, that means I will find the F that will minimize the index. Alright, the index, for example, if the index like this is my index, this is my F, and this is my J. If I partial F, partial J equal to 0, that means I get this there. Partial F, partial J equal to 0. Agree? So if I choose F such that partial J, partial F equal to 0, that means that F, that's the F here, will minimize my energies. Agree? That is the F or the F. Now you have to watch out. I have this one here because J cannot go negative. Can J go negative? Can system energy go negative? No. Can control energy go negative? No. Have you heard about negative energies? No. Right? So because the energy cannot be negative, the cost index cannot be negative. If you get a negative cost index, then it comes in must be wrong. All right, we have another question. So in this, we have only one point, which is the minimum. Can we have a multiple point? What is the minimum? All right. So for example, can I have an index, the cost index like this? J, and this F. Now, can we have the cost index like this curve? That means I have I will have two minimum, one at this point, another point. See, that's the question you might have in the real final. You can listen carefully. That means, is this f is unique or not? F is unique or not? Okay. We answer that question very soon. Now, this is the beauty of cost, the beauty of optimal control. If optimal control gives you multiple solutions, that won't be optimum anymore. Right? So it has to be somewhat, it's unique. If not unique, then it's not called optimal because you got many optimal solutions. We'll prove that later, very soon. All right, let's look at this. But if you look at this carefully, here, the index here. Okay, wait there, go next. See, unique solutions. Now, our control gain solution will be BRF squared plus 2ARF minus B. If you look at carefully, go back. If I want that equal to 0, all right. Erase that. There's some very, very basic concept here now. You have to be careful. Because a partial f, partial j, partial f equal to 0, that implies what? That implies the BRF squared plus 2ARF minus B equal to 0. Agree? Right? Because A plus BF cannot be 0. And if we want to have partial f over partial f equal to 0, that means that BRF squared plus 2ARF that equal to 0. Now, these equations, how many solutions we have for f? No? How many? These equations, how many have? 2. Alright? So now the question is, both 2 are the solutions, or one of them is the solutions. Right? Okay. Now, solutions. We have that. Solutions. Now we have 2 solutions. Is minus A over B, parenthesis 1 plus and minus the square root A 1 plus B squared over RA squared. If we are allowed to have only one solution, that means one of the solutions is not right. And which solution is right? Which solution is wrong? Okay, so that's you gotta watch out here. Now I'm talking about when A less than 0. This is just only I'm proving either plus or minus is the solutions. So when A less than 0, that means when the system is stable system, R going infinitive, then both solutions will become like this. In the plus sign, F equal to r going to infinity, that means this term equal to 0, right? When r going to infinity, I have, what we mean r going to infinity? R going to be infinity, what does that mean? What do we mean r going to infinity? Look at our j index. Our index is equal to have 0 going to infinity, then I have x squared plus ru squared dt, right? R going to infinity, what does that mean? That means my control force. The control force is the one I'm looking at. I don't care much about x squared. I care my control force. What does that mean? I want to save the control energies. I don't want to use too much of my control energy to control the system. Because I'm weighing heavily on my U. Like in space, you always try to save as much energy as possible from your thrusters, right? If you don't save, you don't minimize that energies, then when your gas all gone, you have no more control. Agree? Okay. Now, that's what it means. When R going to infinity means I want to have U is going to be my concern for the control. Alright? When I do that, then my solutions. You look at these two solutions. The plus sign, then F equal to minus 2A over B. The next sign equal to 0. That means what? When I say I don't want to use much of my control energy, that means what? Again, one of the solutions is gain equal to 0. Just don't control it. Then I don't use my control force. Agree? And then another solution will be 2 minus 2A over B. However, these solutions, what does that mean? That means A plus BF, if you look at BF, then A plus BF equal to minus A, right? Not true? Then that means A plus BF minus A, but however I assume say A less than 0, so minus A larger than 0, for A less than 0. Then what does that mean?